Before we start, I just want to read a quote that a student of mine told me like a year ago. So, Israel is strange. You can be at war with rockets falling into the Aviv, and everybody will visit the coffee shops if nothing happened, but get one day of rain and everything shuts down. Everybody will get them out. Right? Nothing works. The stoplight shut down, everything is in traffic.
There's no traffic lights.
No traffic lights.
Now taxis don't work.
But war. Okay. So I hope everybody is well. I can see that the turnout in the second week is somewhat low, but that's fine. Only to be expected. Yeah. So just to remind you, we have the academic schedule in the Moodle, okay? And in the academic schedule, you can see that next week we have a quiz. Okay? So I told you we have 3 quizzes in the lessons. Okay? We have the dates, right? We have week 3, week 6, week 9. The quiz will contain 5 questions, as I said. 5 questions, all close-ended. Okay? All theoretical. And they will contain material from week 1, this week, and also the week 3. It's going to be multiple choice. Yeah. So it's going to be in the last half hour of the lesson, and it's going to contain material from that lesson as well. Okay. Basically my lessons, but obviously there's a large No, in the lesson. Okay.
So you're going to finish teaching
in my again? Yeah, we'll finish teaching like about what is it, like 1:15, and then we're going to
And we're going to be quizzed on what you just taught us.
yeah.
We're going to be quizzed on what you just taught us.
Yep, as well.
So on the syllabus, it was like 75% exam, 20% homework.
It's 5%, 10% homework,
Yeah.
10%.
There was 10% missing. That's what I'm trying to say.
Okay,
No,
so
no.
we'll fix
So it
that.
was like,
We'll fix that.
There was extra 5%.
For everyone.
We'll fix that. Okay. So I want to start today. And today I'm going to talk about, one last thing, there is no air conditioning due to all the problems. So we're going to keep the doors open, but so all you who are hot, I empathize. I would prefer to have air conditioning, but that's the way it is. Okay guys, let's start. So today I'm going to talk about hypothesis testing and what I call the magic of statistics. So what do I mean when I say that? So last week we talked about this tension between the sample and the population. Right? So there's this small sample that we take, and from that we have to conclude something about the population. Okay? There's a big leap there. So today we're going to talk about how do we do this leap. Now, to do that, I want to give a small example. We have 2 hats. This one's my wife, this one's my friends, and each hat contains balls. Okay? And one, there are black balls, okay? Only black balls. And the donkey one, there's only orange balls. Okay? So black balls, orange balls. I will need a volunteer from the first row. Okay? Close your eyes, please. Okay? Take one ball from the hat in front here. Okay? Okay, open. Which hat is in front? Okay, the orange one, right? Everybody listening? So we have 100% orange balls in this hat, 100% black balls in this hat. So obviously, when we draw an orange ball, it means it came from this hat. right? We're 100% certain that it came from this hat. Okay, close your eyes again. Sorry, open, sorry. Now I'm going to do a small change. So now I'm going to take one orange ball into this hat and one black ball into this hat. Okay? Now close your eyes again. Okay. Open them. So which hat did this come from? Show the class. This she got an orange ball. Which hat did it came from? But if you had to guess without seeing me holding. Okay, so if I would I close my eyes and I take one ball, and I see this orange ball, I would say that it probably came from this hat, right? Probably came from this hat. Why would I say that? Because most of the balls here are the orange balls, right? So it probably, that's my best guess, it probably came from this hat, but I can't be 100% sure. Okay. And in this small demonstration, we just did inferential statistics. Okay. So let me explain why. This is basically the same. So we have red hat and blue hat in this example. If we got a red ball, definitely came from the red hat. Blue ball definitely came from the blue hat. But if we have 95% red and 95% blue, if we got a blue ball, it probably came from the blue hat. So, inferential statistics in hats. Okay? In statistics, we take a sample, one sample, and we describe it. That's the ball. Right? We take one ball. We ask what is the likelihood to get this sample from a certain population. That's the hat, right? We ask, did this ball come from this hat? And we ask, what's the probability that it came from that? If it's unlikely that we got a certain ball from a certain hat, we would say, okay, it probably came from a different hat, meaning a different population. And that's all we do in statistics. Okay? We take a sample, we describe it, and we ask ourselves, what is the likelihood to get this sample from a specific population? And something that's a bit unintuitive, we want the result to be unlikely. Okay? We want to say it's unlikely that this ball came from that hat. It probably came from a different hat. Okay, so that's just talking to your intuition. Now we're going to do the actual thing, and we're going to talk about how we're going to build this distribution. Okay, any questions so far on this example? Okay. So what do we need to know? We need to know the distribution in the H0 hat. Okay? The H0 population. Now here it was very easy. I told you, you saw the amount of balls. I didn't even say it's 10 balls in each hat. Okay, so we had 10% to get this black ball from the orange hat. So we need to know the distribution. Based on the distribution of the hat, we figure what's the likelihood to get our result. But of course, we don't deal with balls, we don't deal with black or orange, blue or red. We're dealing with continuous variables. So instead of this hat, we need magic of animation. Distribution. Okay. We need to understand what's the distribution in the population. So what we need to describe this distribution. Remember what this distribution means? This is a continuous variable, x value, and this is the amount of people I get in that value. Okay, so this is a normal distribution, right? So we have the most values will fall exactly in the middle, and the less and less will be in the sides. So what do we need to describe our population? We need the shape. That's an important factor. We will always use normal distribution. Okay? In a moment, you probably remember how we get a normal distribution, but in a moment I'll remind you again. So if I get a normal distribution, I need two more things to understand my distribution completely. I need the mean of the distribution, okay, or mu, right? Parameter to describe the mean of a population. And I need the standard deviation. Once I know the shape, the mean, and how wide is my distribution, I know exactly what this looks like. Okay? So with these three, I will describe my hat. Yes? Again? The distribution. If I know that the shape of the distribution is normal, I know which value it goes around, right? What's the center of the distribution? And I know how wide is my distribution. I can describe the shape of the population. Okay, so that's our first task. We want to describe our H0 hat. So let's take a simple example. Okay, again, not a good research, but it will help you understand it in a very simple manner. So, a researcher claimed that NBA players are taller than the general population. Seems like a fair claim, right? An easy claim to make. So we have the H0 population, the hat. We have the mean of the population, 1.7. Let's decide that the mean height is 1.7 meters. And sigma, the standard deviation, is 0.3. And we have different people in the population, right? So I have people who are 2 meters tall, 2.3, 2.6. Actually, it's 2.55. And that's 3 standard deviations above the mean. And I also have shorter and shorter people, right? And this is the actor Mini-Me, and he's actually exactly 0.8 meters, 80 centimeters. So this is my hat, this is my distribution. Now I'm going to show you that in a normal distribution, we have this very nice property that we can use, that we can know what is the likelihood to get each and every result. Because it's a normal distribution, I know that only 3% of the population here are taller than 2.3 meters. And I know that 16% of the population are shorter than 1.4 meters. For each value, I know what's the probability to get this value or something more extreme. Okay, so I have my hat. Now, the researchers sampled one NBA. Okay. So, right, LeBron James, if I'm not mistaken. He's 2.2 meters, 3 centimeters. Okay? So now, we're looking at our sample. We're comparing our sample to the distribution. And we see there's about a 16% chance to get this sample from this distribution. Okay? Now we have to decide, is it likely to get this result or unlikely? Now, who will decide what's likely or unlikely? We will decide. Okay? We know that it's exactly 16%. Now, we have to persuade people, right? If the researcher says that NBA players are taller, and then we will say, look, there's only a 16% chance to get this result from this population. So some people will find it convincing, other people won't. Usually, we have a norm. We decide as researchers, we decided sometimes a long while ago, that 5% is enough. Okay? So 16% is not very convincing. Any questions about this process before I continue to the next slide? It will summarize. So there is a 16% probability of finding such an extreme result or a more extreme result. So what happened? We took a sample.
Wait, how
Yeah.
did you calculate the 16%?
So this is actually
Because it's like no,
right. It's a property of the normal distribution. That's why we always want to use a normal distribution. Because in a normal distribution, we actually know what's the likelihood to get each result. So we took one sample. Yeah, sorry.
What are you referring to with the 16% alpha?
Okay, so let me try to summarize it, and maybe if it doesn't work, it still doesn't work, ask me again. So we have one sample, okay? We compared it to a known normal distribution. Okay, so one sample compared to one half. Based on this distribution, we calculated what's the chance of getting this result, this specific result. We concluded that the probability to receive this result is 16%. Why is it 16%? Going back, because if I place LeBron James in this distribution, okay, and I know that there's 3% of the people who are taller than 2.3, and I know there are 16% of the people who are taller than 2 meters. Then LeBron sits here. That's the point where he sits. And then from this point onward, we say, okay, there's about 16% to get this result, right? Or a more extreme result. Does that sit better now?
Which is where he falls on.
Exactly, exactly. So we got 16%. And I've written down that p-value equals 0.16. What's p-value? Probability, right? It's just another way of saying what's the probability. We consider a result to be unlikely if the probability is less than 5%. That's the alpha. Right? Someone a long while ago decided that 5% is an unlikely result. So this result is a likely result. It's likely to get a result of 2.03 from the known population. I see the confused look. This result is not considered extreme enough. Extreme enough for what? Extreme enough. Exactly. It's not extreme enough for us to conclude that NBA players are not from this distribution. Okay? In order to conclude that NBA players are indeed taller than regular people.
How do you decide when it's extreme enough or not?
That's exactly the alpha. Right? We always look for this p smaller than 0.05, right? So the 0.05, that's what we consider extreme. But there's a problem here. The researcher only sampled one NBA player Really? Only one person to base your entire conclusion on? What's wrong with sampling one person? So, we usually take a sample of at least 30, not one. Why is that? So, the first reason is that an average is a better measure than a single result. Okay. When you take an average, you consider an average, a group of people, to better reflect whatever we're trying to decide. It's a better measure than one result. Also, we have a trick. The central limits theorem that you've learned about last year and you learned about in the recitations again today, this week, says that once we sample more than 30 people, even a non-normal distribution will become normal. What does that mean? In a second. Okay, in a few slides. And eventually, we take a group of people, a large sample, because it's easier to reject the null hypothesis, and that, again, doesn't fit well yet. I'm hoping it would in a few slides. Okay. So I know a lot of questions remain unanswered. Bear with me. Okay. So let's take a sample. Instead of taking one participant, now we're taking a sample of 36 NBA players. Now, the mean of this sample happens to be exactly like LeBron James' height, 2.03 meters. Okay. But notice something. This is a distribution of single results, right? This is one person, one person, one person, one person. Now, when we take this sample and take the average grade, this does not fit here because this is a distribution of single results, but we have an average. It's like trying to shove a square into a circle. Just doesn't fit. We have to have a distribution, not of single results. We have to have a distribution of averages. I know it's hot in the room. I see people waving. So we have to find a distribution of averages in order to compare it. Okay. So how do we draw a distribution of averages instead of distribution of single results? So that's the idea of the sampling distribution. The sampling distribution is a distribution of averages, okay, distribution of samples that will occur if we take endless samples from the population. Okay. Right, you've learned this last year. When I was studying, I never understood how do we take endless samples from the population. It never made sense to me. What does that mean? Taking one sample, one sample, one sample, one sample. How do we do that? So the thing is, we don't really have to do that. All we need is a few mathematical rules to understand how does the original population transform into the sampling distribution. So what will happen if we take a sample of 36 people out of the general population? So here are 36 people out of the general population. Okay. You have some people who are really short, some people who are really tall, but most people are basically in between. Right? What's going to be the average score? Let's say about 1.5. Okay. Yes?
So the two dots on the
Right, exactly. Exactly. So one person, 36, and I'm taking the average score. So here we have a few more short people than tall people, so the average is 1.5. Let's take it again. And now we have a few more taller people than shorter people. Okay? Now notice I sampled really tall people. This dot is supposed to be 2.5 meters. Okay? But the average score is a lot closer to the middle, right? Because these extreme scores are tempered, they're moderated by these scores. So eventually, I get this thing, right? Above the average, but still closer to the average. 1.5 is the previous one. This is the first one. We got 1.5. This is the second one, 1.9. So what will happen next? Look at the animation. Let's take one more sample, one more sample, one more sample, one more sample, and we'll get this. So slowly we'll get more and more and more and more and more and more. And surprise, surprise, this looks like a normal distribution. So if you do a simulation of what the distribution of samples will look like, it will look like this. Now, what's like this? First of all, it's normal, right? It's a distribution of averages. Okay. Its shape is normal, which is good because we like a normal distribution. What about the mean? What's the mean of this distribution? What do you say? Exactly. It's exactly the same, right? The most likely result for a sample is exactly the mean of the original distribution. And what about the standard deviation? Did it change in any way?
Yeah.
It became smaller, right? Why did it become smaller? Because it's less likely to get 36 people who are all this tall. Because we take a sample of 36 people instead of one person, then the averages are closer to the mean of the distribution. So the next slide we're going to describe how small. And then what do we have? We have the shape of the distribution. We have the mean of the distribution. And we're going to have the standard deviation of the distribution. So of course we can't take endless amount of samples from the population. Okay? What we can do is to describe the sample distribution. Okay, any questions? Okay. I'm not entirely sure that everything went clear, but that's why we have the elucidation as well. So, the shape. So, a sampling distribution will be normal if the original population is a normal distribution, or the sample size is 30 and above. So, if the original population is this, and the sample size is 1, we'll get this. The sampling distribution will actually be a mirror of the original population, right? Because think about it, the distribution in the population is endless samples of single people. One person, not single, single observations. If you take endless samples of single observations, you just make a copy of the original population. If we have a normal distribution and a sample of 30 people, we'll still have a normal distribution, but it's going to be thin. If we have a non-normal distribution, distribution, this is an equal distribution, right? Then, and n equals 1, okay, we're going to get, again, a mirror of that. But if we have a non-normal distribution, right, and this is a binormal distribution, if we have enough participants, the sampling distribution will become normal, even though the original distribution was not normal. Okay. Yes. it's supposedly a distribution. Okay. So think about it this way: it's an equal distribution. The likelihood to get each result is exactly the same. Okay. Here we have a larger likelihood to get this result, and less and less and less likelihood to get each other result.
So it's still normal?
So this is not normal. Okay. So if we have a small sample size, we have to know that the original distribution is normal. Okay. Otherwise, we can't use it. But if we don't know that the original distribution is normal, and we have a sufficient sample size, it won't matter. Okay. So either we have a normal distribution in the population, or we have enough participants for us to create this normal sampling distribution. Okay, so the sampling distribution is going to be normal, or very close to normal shape. Next step. So that's something I already said. Of course, we cannot take infinite samples, but all we need is the shape, the mean, and the standard deviation. So because the mean remains the same, the next step is that we need the standard deviation. And the standard deviation of a sampling distribution is called a standard error. When I say standard error, being Israeli, I never say error as it should be. Error. It doesn't work. So I'm going to say error, and you're going to be okay with it. So standard error. And it equals to sigma, that's the standard deviation in the population, divided by the square root of n. Our sample size in this case was 36. We're going to divide by the square root of 36. And that's very nice if it happened to be like that. Okay. It's very easy to calculate the standard deviation of the sampling distribution. Now, this is a reminder to myself and to you. Whenever you see these kind of formulas, these kind of letters, always write down what it means. Okay? Don't get confused. Don't get a blackout. Okay? Just write the population standard deviation divided by the square root of the sample size until you see this sigma, this small sigma, and it makes sense. So in our example, n equals 36. Sigma, the distribution in the population, was known to be 0.3. The standard error, 0.3 divided by the square root of 36. So 0.3 divided by 6, so 0.05. So it was very easy to calculate the standard error. So we have the shape, we have the mean, we have the standard deviation. So this is our sampling distribution. Much thinner than the original one. And this is, again, this is our hat, right? This is what describes the likelihood to get one sample out of the population. So now we have this. Now look at these results. The mean is 1.7. Okay. 1.8 is 2 standard errors above the mean of the population. 1.6 is 2 standard errors below the mean of the population. And now that we can take our sample and compare it to the sample distribution, we see that the likelihood to get this result is very, very extreme. Okay? It's a very small likelihood to get this result by chance. And that's exactly what the z-score will tell us. The z-score will tell us how many standard errors is our sample compared to the mean of the population. So we have our sample, x bar, that's the mean of our sample, minus the mean of the population. Okay, so we have a difference of 33 centimeters. How many standard errors is 33 centimeters in this distribution? So we divide 0.33 by 0.05 and we get 6.6. So this result is 6.6 standard errors above the mean of the distribution. But what does that mean? So 6.6 sounds like a lot, but let's give a specific value. So in hypothesis testing, we choose a critical value to represent an extreme result. Beyond that point, we consider the result unlikely. So this is the critical z-score in a two-sided test. And this is a critical z-score in a one-sided test. Okay. And we see that this result is more extreme than the z-score. Okay. So if we summarize, we look at the sample, we compare it to the distribution, and then we say, based on this value, and based on the finding that our sample is more extreme than the critical score, this is an unlikely result to come from this. It's unlikely that it came from this hat. Sorry, in this case, it's unlikely that it came from this hat. Okay? It's more likely that it came from a different hat. Meaning that NBA players came from a different population. So from this one sample, we can conclude aliens, right? Exactly right. So from this one sample, we can conclude that they probably came from a different population. That NBA players and the general population are somehow different. And with this, we bridge the gap. We took a sample, and based on the information that we have, we somehow bridge the gap between our sample and the population. Yes?
It's just confusion, like population is almost like a different spectrum. Like you could say, I think like maybe that's the confusion when you learn about this. Like, you know, like you just made a joke, aliens. Like it's not another population, it's us. It's confusing. It's almost like another. It's just not a different spectrum. You would say.
Right.
I feel like that's more easy to understand. I think that's the confusion when you learn about this because you kind of like population of the earth and kind of mixing it
Yeah.
population. Then I get confusion on that.
Yeah, it's a good point. So what does that mean that they came from a different population? Okay. Obviously they didn't. They're all people. But what we're saying is there's an organizing rule here, right? There's something to make the distinction between NBA players and other people. Now, of course there's something to make this distinction because NBA players are chosen for being tall and athletic and stuff like that, but being tall as well, right? They're a select group. So of course they'll be different. Okay. But again, population is not only a population of people. In this case it is, right? The distribution of people. But it's also something abstract. When I say that NBA players are taller than the general population, it means that there's something systematic is going on. I can give you other examples. Coffee makes you less sleepy. Okay. So coffee has something systematic in it to make you less sleepy. So it's not exactly that they're different people from a different population, but there's an organizing rule that makes them taller. They're not. Okay, I think maybe it was a bit clear. Okay. How are we? Yes. Okay. So the researcher in this case said that NBA players are taller than the general population. That's a one-sided hypothesis. He's looking only on this side of the distribution. He could also ask, are NBA players different from the general population? In that case, he would say, they might be taller, they might be shorter. And then he would look either here or here. Now, when we look for a one-sided hypothesis, we take a risk, right? Because it might be that NBA players are shorter, okay? But we're only looking here. So we make a risk, but I'll show you in a second why this risk sometimes is beneficial. Okay. So let's take another step and talk about the truth. So I told you last week that I have a very romantic point of view about statistics, and I told you that we're here to look for the truth. We won't find it, or we won't be certain that we find it, right? That's what we said. We're never 100% sure. We always leave some probability that we were wrong. But we are looking for the truth. And there are two options. When we say NBA players are taller than the general population, there are two options. Either NBA players are taller than the general population, or they are not. I framed my hypothesis to have only two options. Either I'm right, and the truth is that they are taller, or they're not. Now, these are two very distinct, different possibilities. Okay? Now, we don't make our decision based on what's true in the world. We don't know what's true in the world. We make our decision based on our sample. Now, that makes us, because we make a decision based on our data, this decision could be either right or wrong. Right? What's a wrong decision? For example, there's a pharmaceutical company doing research about a new drug, and they think from one sample, one research, that their drug works, right? Heals something, a tropical disease. But then people keep taking it and taking it and taking it and taking it, and it doesn't work. And eventually, what they found out is that the drug doesn't work. So the original researchers were wrong. Okay? They took one sample. The sample told them that it works, but they were wrong. Okay? There's not necessarily misconduct or something unethical. Okay. So let's look at the researcher's decision. One time when we say that H0 is correct, and one time when we say that H1 is correct. Okay, so We don't know if H0 or H1 is correct. If we would know, it would have been nice. We wouldn't have to do research. But let's imagine for a second that H0 is correct. So H0 is the original distribution. Okay, we know how it looks like. And we have this rejection line. Okay. Now, if H0 is correct, okay, only if H0 is correct, then if I took a sample that happened to come from this small tail, this is where I would say, oh, NBA players are taller. That's what my sample says. But H0 is actually correct. Okay? They came from this. There's a small likelihood to make this mistake, but there is a likelihood to make this mistake. Right? What's the likelihood to make this mistake? 5%? Exactly. Usually we'll use 5%. Throughout this course, you always see it's 5% unless stated otherwise. So I have a 5% chance of making this mistake if and only if H0 is correct. I want to give it one more point of view. What does that mean that we have a 5% chance? Now, this is the distribution. Okay. The most likely result in this distribution is the mean, right? The most likely result to get from this distribution is the mean of the distribution. But there's always a chance of getting an extreme result. What's an extreme result? This is an extreme result. Okay. So this alpha, if we fall in this section, and we make the decision to reject the null hypothesis, and we're wrong to make that decision, this is called type 1 error. Why is it called type 1, and how do you remember that it's called type 1? Because it's the most serious error that a researcher can make. This is the most serious one. Yes? So how do we remember that this is called type 1 error? What's this? This is when H0 is true, and we think that it's not. And we say to the world, look, world, we've shown that H0 is not true. Yes?
Or did you use A for arrogance last year?
Again?
A for arrogance, you used. Our research assistants used that. A for arrogance.
A for arrogance. Nice.
Yeah.
Nice. Okay, but, yes. Exactly. Now, why do we call it type 1? Why does that get priority? Why is this the most serious, the more serious of mistakes? Right.
Rather be the opposite.
Right, very good. So, we assume that H0 is correct. When we go in the world, we assume that nothing is systematic. Everything is chaotic. Everything happens by chance. Okay? That's our assumption when we go to the world. Now, when we find something in this area that's very exciting, we found a significant result. Now we're going to publish an article. Now I'm going to persuade people that something in the world is systematic, even though I'm wrong. Now, NBA players is not a good example here. But think of a drug company, right? The drug company producing a drug based on their one research, and the drug doesn't work. Right? That's a very serious mistake. They persuaded people that their drug works, but it's not working. Okay? So that's why it's type 1 ill. You change the way people view reality. Yes? So alpha is just the type 1 element. That's exactly what it is. So what's the alpha? It's a value that we choose to describe an unlikely result. So we say that anything from this line onward is considered an unlikely result. So we decided that. We decided that's considered an unlikely result. Yes?
Do you have the chart by any chance from last year that explained it says 1.2?
You'll have it in the presentations. Now, this area is called the confidence level. Now, it's not a very interesting area. Okay? This area is where H0 is true, and that's what we found. Okay? That's not interesting. But I had one case where I did my own research with my advisor in my MA, and we did one experiment, another experiment, the third experiment, and nothing came out significant. And then she said, "Well, that's good. Now we know it doesn't work. Okay? Now we know that we were wrong. That's good to know. Now it won't get published, but at least we know. Right? At least we found out that H0 was correct. Okay, so that's what happens when H0 is correct. Okay, there are only two options in this case. Either we don't reject H0, and then it's a boring result, but it's true, and we didn't make a mistake. Or we did reject H0, and then we made a serious mistake. And this is why it's very important to have replications. Okay, I don't know if you know, but the world of research in psychology was there were a lot of problems recently. A lot of people tried to replicate various studies and couldn't. Now, the problem is that if you don't replicate your studies, you basically have a larger chance of making a type 1 error. If you take, instead of one ball, you take two balls, and both of them come out the same, then you're feeling safer about concluding what is this hat. Okay, good. This is what happens when H0 is true. One more thing about this. Before we take our sample, we decide on an alpha. Okay? We decide what's considered an unlikely result. So alpha is always, in our case, 5%. But after we sample, we have a different value. We have a value called p-value, right? What's the probability of getting our specific sample? So in this case, the result is so extreme that we would say that p-value, is less than 0.001. The probability that this sample came from this distribution is less than 0.1%. Now, the alpha was 5%, okay? But the actual probability, p-value, was not 5%. It was less than 0.1%. So there's this difference between alpha and p-value that's sometimes missed. We always try to find out whether our p-value is smaller than alpha. Whenever this value is less than 5%, we'll be happy enough to reject the null hypothesis. Now think about this case. Okay? If H0 is true, and NBA players are not taller than the general population, okay? Try to imagine that. Try to imagine that all the NBA players are just regular people, regular heights, okay? And it's just imaginary. We all imagine that they're tall. Okay? The likelihood to get this result by accident is very, 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 very small. Okay. So what? Yes. Right. Exactly. Okay. Now the thing is, it's more impressive if you decide in advance that your alpha will be very small. Right? If you say in advance, I'm not going to take an alpha of 5%, I'm going to take an alpha of 1%. Okay. That's an impressive move. And some people will appreciate that. But if your result is this, it doesn't matter what's your original alpha. Okay? I guess I'll close the door even though it's warm here. Now we're in the sound. Okay. So if your p-value is less than 0.1%, it doesn't matter if you chose an alpha of 5 or 1%. Okay? Your result is equally impressive, whether you chose an alpha of 1 or 5%. Okay, so let's talk about what happens if H1 is correct. Okay, H1 is correct, that's the more intuitive in this case. NBA players are indeed taller than the general population. So maybe this is H1. Why is it in dotted lines? Do we know what is the average height of NBA players? No. The average height, we know, basically because there are statistics. In this case, we don't know. So, we don't know where H1 is located, right? We always see these two mounds, two distributions sitting one against the other, but we actually don't know where H1 is located. It could be located here, or it could be located here. Okay. So we don't know where H1 is located. It would have been nice if we would know, but we don't. That's the problem, right? If we would know, we wouldn't have to do research. So we have H1, which is kind of imaginary in our head. We don't really know where it is. And here we have also two sections. Okay? We have the beta, which is the type 2L. What's type 2L? It's first of all, it's the least problematic L. So this is, let's say this is the sample distribution of NBA players. And by chance, we sampled from this area. So we would not reject the null hypothesis. And we would say that the NBA players are not taller. Now, why is that not that big of a deal? Because, again, we assume that everything is chaotic, nothing is systematic. If we find this, we didn't change anyone's opinion about the world. Everything remains the same, right? We go out and we say to some people, hey, we did a research and we found that NBA players are not taller. And they would say, yeah, that's what I assumed all along. Yes.
Couldn't it be problematic if I guess we didn't find a careful answer?
Yeah, okay, so in that extreme case, that always comes up. In that extreme case, it is, of course, problematic, right? That you could have found the one thing to save the world, and you didn't. But in terms of science in general, because you didn't change anyone's opinion about the world, it's considered that it's safe. Exactly. Also, if you think about it, if you do this mistake, you won't get to publish a paper, right? No one will publish a paper with, oh, we didn't find a significant result. Okay? That's actually a problem because that's why once you publish a paper, it's very problematic to now convince people that the original paper was wrong. So that's type 2. NBA players are indeed taller, but we didn't find that result. And this is the best area to be in. This is the power. Okay? Now it has an impressive name. Power. Now, this is the area we want to be as large as possible. Because this is where, basically this is where we publish an article. Okay. This is where H1 is correct, and the A pairs are indeed correct. And also, our findings reflect that. Okay? So, NVA pairs are taller, and our sample is somewhere here, and we found out that our decision reflects the truth. That's the summary. So we said that we don't know the mean of the distribution of H1, and unless we do know the mean of the distribution of H1, we cannot calculate the exact size of either type 2 MO or the power, right? The fact that we have this area here and this area here, it's hypothetical. It could have been here. Right? In this case, we have only a small power and a lot of type 2 MO. So we can't calculate the exact size of the power. What we can do is we have a few ways to increase the power. Yes. Okay, so power is assuming that H1 is correct. Right? Now we're in the world of H1. H1 is correct. And we found a sample that correctly reflects that. Right? We found a sample that NBA players are tall. So we were correct on the decision. We correctly rejected the null hypothesis. Okay. So we have a few ways to increase the power. If we have more power, what does that mean?
Higher probability.
Again, if I have more power,
More likely to reject the issue.
exactly. Okay. If I have more power, I have a higher likelihood to reject the null hypothesis. Okay. Less chance. I feel. Next time I'll know. Okay. One more thing about type 1 ill, type 2 ill, confidence level, and power. If I tell you that H1 is correct, what is the likelihood to make a type 1 ill? But I told you that H1 is correct.
Zero.
Then there's no chance of making type 1 ill. Let me repeat that for everyone. If I tell you that H1 is correct, there's absolutely no way you can make a type 1 ill. Okay? So let me give you an example. So the drug, okay? The pharmaceutical company, and I tell you from some high point of view, I came from the future, okay? This is exactly the Back to the Future thing. So I came from the future, and I tell you, this drug works, okay? Absolutely. Now, if you're doing your research now, the original research to see if this drug works or not, you can't make a type 1 MO because you're not in this world. Okay? You're not in the position of making type 1 MO because the meaning of a type 1 MO is where H0 is correct and you reject the null hypothesis. So if I tell you that H0 is not correct, you can't make type 1. Also, if I tell you that H0 is correct, is there anything that can increase your power? No, because you have no power. If H0 is not correct, nothing will increase your power, because the word power only refers to a situation where H1 is true. Okay? So notice that in a lot of questions, and we'll have questions in the homework like that, that will start with the sentence, assuming that H1 is true, which of the following blah blah. Now this assumption is important, because if you can't assume that H1 is true, you might not have any power at all. Okay. So the more power we have, assuming that H1 is true, the more power we have, the better. We prefer this situation to this situation. Here, this is the power. Here, this is the power. So what can increase our power? Very good that you already gave answers, but let me go over one by one. So I'll have something to do here. So, first thing that we can do is not a very good solution. It will be to increase the value of the alpha. So look at the screen, we have an animation here. All the following slides we have some animations. So this is an alpha of 5%. And now if we move, technology. So alpha was here, and this was the power. Oh, now it moves, and now alpha is 10%. Again, assuming that this is the true distribution of our study, now there's a higher likelihood to find a significant result. Right? Because we sample from this distribution. So we have a higher likelihood to get somewhere from around here. What's the problem with increasing the alpha?
Type 1.
But I told you that H1 is correct, right? If I told you that H1 is correct, there's no chance of making type 1. You're correct. Did you say that? Did you say that?
I said it. I didn't hear the part about we knowing H1 is.
Yeah,
I meant
but-
in general.
Yeah, but you are absolutely correct, because the fact is that we don't know that H1 is correct. We want to believe that H1 is correct, but we don't know for sure. There's one more thing, though.
Nobody will publish your articles.
Exactly.
Yes.
Did he say you increase your beta as well? And the fact that increasing your alpha, so you're increasing your blind spot as well. With the,
Actually,
chance of missing as well.
your beta becomes very small.
Maybe, that's what I mean. So it's like you're decreasing your power, increasing power. Oh, minus where I am.
So you decrease the chance of type 2. Again, if you look at it, that's H1. H1 is correct. Okay, this is the power. This is type 2L. You only increase the power and you reduce the type 2L. Seemingly, that's a very good situation to be in. However, first of all, we don't know that H1 is correct, right? So we might also increase the chance of type 1L. Second, we want to convince people that our study is correct, right? Research is a story. We want it to be a convincing story. We can't choose an alpha that we want just to make it easier for us. We have to convince people by talking with the same norms that people use. As I said, choosing an alpha of 1% is impressive exactly because of that. It's like saying in advance, I'm so sure of my research, I'm so convinced that I'm going to show you they're going to get a p-value of less than numbers. So, to summarize the first slide, when the alpha is increased, it is easier to reject the null hypothesis, but this is not a good method to increase the power because there's also a higher chance of packing them. Again, only if we don't know that H1 is correct. Okay. Yes. So look at this diagram. So this line is the alpha. Sorry. This line is the alpha, right? If we increase the alpha, so this is the power, and this is type 2 error. If we increase the alpha, the power increased, right? Is that clear, the idea that if you increase the alpha, the beta decreases. The power increases, the beta decreases. Now, there's something confusing here. I keep saying the power, but I feel like it's not intuitive enough. So think about it this way. When I say the power, translate it in your head to the likelihood to reject the null hypothesis. Larger alpha, higher likelihood to reject the null hypothesis. Okay? So more power, higher likelihood to reject the null hypothesis. Okay. Here's a better method. First thing is to have a stronger manipulation. Stronger manipulation increases the effect. So what does that mean? So look at the animation. This is the original distribution, but if we would have a stronger manipulation, H1 would travel here. Okay. So this is the original, and this is H1. Okay. Now, what does that mean? Think of the following research. I'm doing a study to examine whether coffee makes you less picky. And I have one group that doesn't drink coffee, and the other group drinks a cup of coffee. Okay. That's an okay study. Now, think about another study. One group doesn't drink any coffee. The other group drinks 6 shots of double espresso. If coffee makes you less sleepy, in which of the cases do we have a better likelihood to find that? The second one. Everyone on board? Right? If I give 6 shots of double espresso, people won't sleep that night. Okay? But if I give them 1 cup of coffee, that's a very weak manipulation. So the stronger the manipulation, the better likelihood to find a significant result. Another example. Just that. I want to see whether hitting people, right, will cause them pain. Sounds obvious, right? But if my manipulation of hitting people will be this, then that's a weak manipulation. It is true that hitting people will cause them pain, but you need a large enough, a strong enough manipulation for you to find that effect. Yes?
Would your sample would be the 6 espressos or 1 coffee, or would it have to be 6 and 0?
That's dependent on design. You can do 6 and 1 and 0. You can have 4 groups, 2 groups. But the stronger effect is by manipulating coffee, yes coffee versus no coffee, with 6 shots of espresso instead of 1 cup of coffee. Now this is a good thing to know for your empirical seminar as well. Because one mistake that a lot of students do in their studies is to use a very weak manipulation, right? I saw studies about, for example, priming. So I want to prime you into thinking about, for example, aggression, okay? And I will use a cross puzzle where you have the word hate embedded somewhere. That's a very weak manipulation. You always find a stronger manipulation to find your effect. Okay? So in general in life, don't use weak manipulations. Okay. Is it clear why the strong manipulation made H1 move?
Polar.
It made it more to this direction, right? So think about it this way. H0 is coffee, doesn't make you less sleepy. H1 is coffee, does make you less sleepy. So the larger the dose of coffee, you'll get results that are more extreme. In the example of the NBA players, think of two possible situations. I wanted to see if basketball players are taller than the general population. Study one, I sample people from the Ramat Gan teenage basketball team. Okay? And the other study, I sample NBA players. Which will have a likelier result to find a significant result? The NBA players, because I'm using a stronger effect.
And then that's why it's really hard to trust anything that is published, you know what I mean? Because you're manipulating what you want, you're saying that simulates the same thing as the population, at the end you're manipulating it to do the results that you're gonna get.
Right, I see what you mean.
But why does that make it harder to trust? They have to write what their manipulation was, and then you can just say, okay, so it'll only have an effect if I drink 96 cups of coffee. But
That's true, but most of the time when people read an article or research study that comes out,
they don't read it.
what do you read? You read the title.
Right.
Coffee makes you less again. Now because we learned about
Oh
it.
yeah, I don't know somebody that should read
No,
it.
it's different, you know? But
That's a
most
very
people-
good discussion.
Not part of the population.
Exactly. The thing is, it's really when you read a headline, it's like we saw last week that men are better in mental rotation tasks. What people think it means, what it actually means, right? So it's very good that you'll have the knowledge to get into these articles and really understand them. Okay, we have two more slides. Reducing the variance of the sampling distribution, not population, sampling distribution, will increase the power. Smaller standard error, more power. Now, why does it mean that we have more power? So again, look at the equation. So this is the original situation. And now this is the situation. Okay. Again, we have this, and if we have a smaller standard error, now if H1 is correct, I almost have 100% power. It means that the likelihood to get a result from this is very, very, very high. Now what would reduce the standard error? First thing is more participants, right? We saw, think of the beginning of the lesson. We saw that if we took a sample of one person, the sampling distribution is really, really, really wide, right? LeBron James was not significantly different from the rest of the population. But if you took a sample of 36 people with the same score, the result now became very, very, very significant. And it happened because the sampling distribution became thinner. So the more participants you have, the more power you have, but because the standard error will be smaller. Another way to get a small sampling error is to sample from a homogeneous population. A homogeneous population. If you try to remember what it means, homogeneous versus heterogeneous. So hetero is different, right? Heterosexual, different than I. Homosexual, same as I. So homogeneous, more, people are more the same. So a homogeneous population. Now think of two examples. Most studies in psychology are conducted on psychology students. One advantage of that is that psychology students are very homogeneous in their responses. Okay? Of course, that's a big problem of what you can conclude, right? But it does make the effects stronger. It makes it likelier to find a significant result. Now, if you have a study that samples from people from all walks of life, now you're going to get a very homogeneous population. So, for example, you want to check something about altruism. Okay? You want to see if people in Israel are more altruistic than people not in Israel. The general value of altruism in the world. I just thought I don't think that's true. It's if you sample from only from people who are in the university, okay, it's the same peer group, right? Similar values. But if you take from the entire population from different situations of life, you can imagine that the original population will be a bit wider. Okay, I felt that this wasn't very clear, so if you have any questions, feel free. Okay, so one more thing. Yeah.
When you sample from a homogeneous population, it wouldn't be construing, not construing the results, but like, isn't it essentially you're going and getting people from the population that you want to be getting them from?
So I'll give you an example where it's not very problematic. So I'm doing cognitive psychology. And I'm trying to find out about basic mechanisms of attention. Now, one of my measures is reaction time. I'm asking people to respond as fast as possible when they see something. Now, psychology students, and particularly psychology students who do the experiments in the beginning of the year, are very, very fast, very dedicated to the task. Now, I once did a study with just people from throughout the university. And it's not that the average was different, but there was a lot more variability. Some people were slow, some people were fast. So it's not that the psychology student had a larger effect, but they were very homogeneous. Everyone was about the same. So in that case, my conclusion wasn't affected by the psychology students themselves, but it was affected by the fact that they were very, very similar. Okay, so if anyone had a problem with doing the homework or getting into the Moodle or understanding something in the bureaucracy of the course, feel free to step in or ask me right now.
No, the SPSS doesn't work.
Because please have on our website.
Okay, so SPSS, I understood it doesn't work in
Yeah, it's more like on now.
It's IDC apps that doesn't work.
IDC app.
Yeah.
So I'll tell you what about the SPSS.
Will it be on the exam?
Okay. So two things. First of all, I'm going to repeat myself because I know that people forget. SPSS on the exam is going to be just one question of an output, right? You're going to just have to read an output. There's no.
Oh, we don't have to do it, already have it, or like.
You just have an output you have to read. That's all. Now about the homework in the SPSS. I know that the abstains doesn't work that well, or sometimes doesn't work at all. I'll try to see if if there's a problem. But my recommendation is do the homework after the recitation. Now, I know that today might be problematic to do it in the computer classes, okay? Because there might be no electricity there. So if that's the situation today, then we'll just excuse you for the SPSS question if you haven't submitted them. Still try to submit, you still have 6 out of 8, right? So you can still get to 5, but of course we'll try to take that into consideration. But usually we'll just ask you if you can't get to SPSS from afar, just do it in the classes, okay? In the computer classes. Okay, thank you.